Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper, Charlie to friends, and I'm a theoretical physicist currently doing a postdoc over in the University of Helsinki in the Helsinki Institute of Physics in Finland. And I'm a cosmologist, which means I study the universe, the contents of the universe, how things evolve, how things interact, cool stuff happening inside the universe. I love being a scientist, I love being a cosmologist, and I love chatting to everybody about all of the cool things I get to study in the universe. I see we have a bunch of the regulars coming in here. Great to see everybody. We have David, Scott, Mito, Paul, Sophia, James. Great to see you all. Welcome back. If you're a regular, welcome back. If you're a first-time viewer, welcome. It is great to see you here. So, for anyone who doesn't know, I messed up my lighting. Now that my lighting has been corrected, that's just so much better now. I only turned on one of the two lights that I needed. Hi, Neda. Great to see a new face. Sorry. Great to see a new face in here as well. Comment and John, as always, good to see you. Comment from David here, David Howden. Good evening, good to see you, David. Do we have two Davids in? We have two Davids in the room now, at least two. Two who have said hello. I'm a welcome distraction from screaming at some code that isn't working. Yeah, I get that feeling. Screaming at code that isn't working is a daily occurrence in certain fields and something that definitely happens way too often. So hopefully I can provide a distraction from your code, and hopefully you will get the code working at some point. Hey, Sina, great to see you. I thought I might see you here today. Welcome to any first-time viewers. Welcome back to any regulars. So for anyone who doesn't yet know, and a reminder for those who do, Cup of Cosmology is an interactive stream. The idea here is that you people can ask me anything you want about physics, about cosmology, about space, about academia, about my life, about my cats. You can ask me anything you want, and I will do my best to try to answer. Now, of course, I don't have all of the answers, but I will do my best to answer the questions that I can answer. So, as some of you have already noticed, there's been a 2-week absence of Cup of Cosmology. I was busy, and I had friends around, and then I was just tired. So that's why there hasn't been a Cup of Cosmology the last 2 weeks. Back today. Next week, there also won't be a Cup of Cosmology because my mum's coming over. So there won't be one next Sunday, but I should be back in 2 weeks. But today, we have 60 to 90 minutes, somewhere in that frame, to answer all of your questions. Scott, thank you for asking about the cats. The cats are doing very well. They've had dinner. They're now, one of them is sleeping, the other is up to mischief, as always. They alternate which one is up to mischief. Sometimes they're both up to mischief. But the cats are doing well. It's still surprising that it's only been 2.5 months since these two guys came home with me, and they've already settled in so well. And I cannot remember a time when I didn't have cats around. So yeah, it's only been a couple days, but sorry, a couple months, 2.5 months. But yeah, the cats are doing really well. They seem happy in their new home. Neda, yes, I recognize you from the name and from the photo. So thanks for dropping by to the stream. It's nice to have you here. It's always nice when I meet people in person and then they show up on the stream. And I'm like, hey, I know you in real life. You're not just a name on the screen. So it's nice to have regulars in here. It's nice to have some new faces in here. So as always, you can ask me anything you want. But there are 2 things that I want to talk about briefly today. You can ask me whatever you want about other topics as well. But there are 2 things I do want to mention briefly. As always, you might have seen some hints for that in the questions that I put on YouTube, the prompts. You might have seen some hints as to what we're going to talk about today. But there are at least 2 things that I want to talk about. And then we can talk about whatever else you want. Question from James here. Did you hear about the superneutrino particle they are talking about? I did not. No. Superneutrino particle? I have not been reading the news lately, but I have not heard about a superneutrino particle. Let's see if I can just pull up something very quickly to see what you are talking about. Superneutrino particle. Let's see, just if I can. Yeah, that didn't immediately flag up any PopSci articles, so I imagine that's not the right keyword. So, yeah, James, if you want to ask me more, if you want to send me a link to that or tell me exactly what that means. But no, I haven't heard about a new superneutrino particle, although there's often things like that people are talking about. Usually, I would guess if we're talking about superneutrino particles, so neutrinos are a type of particle, part of the standard model of particle physics. Neutrinos are extremely light. They travel almost at the speed of light, but not quite at the speed of light. And they can be produced by a lot of different things, for example, supernova. And a good thing about neutrinos is they don't interact much, so they can travel long distances, which means we can often find neutrinos that come from even outside of our galaxy because they've just traveled uninterrupted towards us. There are many detectors, for example, Super Kamiokande, Ice Cube, things like this, that are searching for neutrinos. Depending on the energy of these neutrinos, we can figure out where they're coming from. So without having read anything recently about a superneutrino particle, I would imagine that they found a very energetic neutrino, or maybe a very energetic neutrino coming from somewhere, but I haven't seen the specific news article. But about 2 weeks ago, or 1.5 weeks ago, like a couple days after my last stream, there was an announcement from the Euclid mission about an Einstein ring. So I want to talk a bit about what an Einstein ring is, and I want to show you why an Einstein ring is pretty and why you should care. So this is just to make sure we're all on the same page here. Euclid is a spacecraft launched by the European Space Agency. It launched in July 2023, already 1.5 years ago. And Euclid is trying to study dark matter and dark energy. So Euclid is mapping the evolution of galaxies, or mapping how galaxies look today, and mapping galaxies going back further and further out in the cosmos, which means looking further and further back in time. This allows us to kind of reconstruct how galaxies have behaved over the past 10 million years of cosmic evolution. 10 billion years, sorry, of cosmic evolution. So Euclid is often called the dark detector, or the dark investigator. The dark detective, I think, is the name they went with, the catchy title. So Euclid is this mission that is trying to study dark matter and dark energy. But on its way to do that, it's also taken a lot of other information. For example, when Euclid first turned on, a couple months after launch, so it's positioned at one of the stable points around Earth's orbit, around in the combination of Earth and the Sun. There's 5 like stable points where it's easy to park spacecrafts. Euclid is in one of them, in L2 specifically. And not long after turning on, Euclid took some first images just to kind of check that everything was working the way it should. So these are not the main scientific target of Euclid, but they were images that were taken as kind of a byproduct, or as a getting started package for Euclid. And in one of these images, a scientist who's been working on gravitational lenses for years found something very interesting. So I'm going to show you the image, and then we're going to unpack what is inside that image. So let's see. I just saw a message from David Dunn that it's just a red circle. Oh, it's an Einstein ring, I guess. Great. I was just like, well, why is there a red circle? Hey, Beth, great to see you as always. Okay, so this image that will hopefully come on the screen in a sec. Yes, this thing here. This is what was seen in one of the pre-release images of Euclid, so one of the early images. This is a close-by galaxy, close-ish. It is galaxy NGC 6505, which is 590 million light years away, which means we're looking at how this galaxy looked like 590 million years ago, because it's taken that long for the light to travel towards us. But I think we all want to zoom into the central part here. So let me just zoom in here. And now you can actually see specifically what was found in the center of this galaxy. And you can see here there is this very bright galaxy in the center. So all of these dots that you see in the background are other galaxies. There are some point stars, but most of the things that you can see here are galaxies. And you can see in the center here, we have one galaxy surrounded by a ring. So there's this central one, and then there's these kind of 4 ones around the central galaxy. So we have the central galaxy here, and these 4 bright lights forming almost a complete perfect ring. So this here is the true image from Euclid. We can zoom out again. So this was the, let's see, this was the initial image that Euclid took. And then someone noticed that here in the center, there is, I just tried pointing with my cursor. You obviously can't see that. But in the center of the image, there is this thing here, which is the Einstein ring. Just zooming in again, here you can see again what the Einstein ring looks like. So what is an Einstein ring? That is what I want to answer now. And I'm just going to remove the image. Right, there we go. So an Einstein ring is a very cool gravitational phenomena that is also something that was kind of predicted by general relativity. So there's a couple of things that we know about general relativity, about gravity. One thing that we're pretty sure about is that, or in our current understanding of gravity, objects with mass curve spacetime, and the curvature of spacetime tell objects how to move. So this is this is general relativity in a nutshell. If you have a big massive object, it's going to distort space-time, and everything moving through space-time is going to feel this distortion and adapt its motion accordingly. So this means that we can use the motion of objects to kind of figure out the gravitational field or the gravitational objects close by, because we know that if an object it changes its trajectory, it's probably due to a big gravitational object. So this is the general idea behind gravitational lensing. So gravitational lensing is this idea that light coming from a distant galaxy is traveling towards us, and on its path towards us, it encounters another massive object. So for example, I have a big massive object here. I have a light beam coming in this direction. This big massive object is going to distort space-time, it's going to curve space-time. So this light beam is going to come around here and get distorted due to the gravitational field, due to the gravity bending space-time. Let me show you what this looks like with a schematic, and I'm just flashing an image that is not the one I want to show, but I'm not going to click through my slides individually, but I can jump easily like this. So you just get a random CMB appear on the screen. Okay. So this thing here is a schematic of what gravitational lensing looks like. In the top right, in the background, the top right of this image, in this kind of slice that's zoomed in, you can see a distant galaxy. This galaxy is emitting light, which is depicted with the two white beams leaving this galaxy. Then you can see that we are in the bottom left is Earth. Between Earth and this distant galaxy, there are a lot of other galaxies, there's a lot of other gravitational objects. Specifically, there's this one that has a kind of blue halo, which is just highlighting this is the object we're focusing on. So what you can see here is you have this light coming from this distant galaxy, these white beams. As these white beams reach the massive object, they are distorted around this massive object. Once these light beams reach us, we reconstruct them to be backwards. We draw a straight line backwards. So we do this kind of orange arrows here. The orange arrows is us saying, okay, this is where the light probably came from, because the light was distorted, but we see light coming in a straight line. And then from these orange arrows, if you reconstruct them, you see we get these lens distorted versions of the galaxies. So this is known as gravitational lensing, and this is a phenomena that is very well studied in the universe. We've been able to see many, many, many examples of it. Do I have the right image here? Let's see. I don't remember what's in my slides. We're either going to get a random image or, yes, we got exactly the image I wanted. This is the very famous, well-known deep field view of the Hubble Space Telescope, where Hubble Space Telescope just stared very intently at one corner of the sky for a while, or one patch of the sky, and it managed to photograph millions of galaxies or thousands of galaxies. And you can see here a lot of these galaxies are distorted. They have this kind of lens-like structure to them, caused by the gravitational lensing. I should also have one here about, no, that's not the one I was looking for. Let me try and go back. I haven't checked what's on the later slides of my slide deck in quite a while. So now we're just kind of hoping that the one that I want is indeed the previous one. Let's see. Give it a sec to load. If not, I'll come back to, yes, here we have another one from the Hubble Space Telescope where you can see this lensing effect more clearly. You can see there's a lot of distorted galaxies here, a lot of galaxies that present this kind of lensed effect. And this is due to the gravitational lensing that I was just explaining. Let's see if I have one more, because I might have the JWST one here as well. I do not have JWST. Okay, so basic idea here, light comes from a distant galaxy. On its path towards us, this light is distorted by a close-by galaxy. By the time it reaches us, we have a distorted light beam. So the light that reaches us is distorted. We reconstruct it back and we see a distorted version of the galaxy, because the light on its path towards us was distorted or moved by a big gravitational object. So usually when we think about this gravitational lensing, we think of things like the deep field view that the Hubble Space Telescope did, so this one here, where you have these small lens galaxies. If you look just left, kind of imagine that you want to stare at the thing at the center, think of it as a clock, look around 10 o'clock, and you can see these really distorted lines. So these are the galaxies that we're talking about that have been lensed. So the difference between those and a Einstein ring is basically the relative position of the galaxy that is being distorted and the galaxy in between that is distorting. And what often happens is these are not completely aligned with our field of view, so they're slightly off, and then you just get a bit of the galaxy. But if you happen to have our line of sight, so us, observer here on Earth, the distant galaxy, and the thing in between that is causing the distortion, if you have all of these in exactly one line, then instead of getting just a distorted part of the galaxy, you get a whole ring of galaxy. So it's basically like holding up a magnifying glass to the faraway galaxy. This close by galaxy is directly in front of the faraway one, which means the light from the faraway one gets completely distorted and reconstructs a ring. So looking again at this image here, which is the Euclid image, you can just look at the zoomed in version, which is this panel that appears called the Einstein Ring. In the center, you have the close by galaxy, that is the one doing the distorting. And the four bright spots almost forming and the kind of distorted circle you can see around it, the ring you can see around it, is all one galaxy that has been distorted. So this image contains two galaxies. The zoomed in version contains two galaxies, the central one and the distorted one that forms the whole ring. So the ring is one galaxy that's had its light distorted or warped by the other big gravitational object, which is very cool. As Paul is just saying, here in space, you can see around corners to see what's behind a huge galaxy by looking at the Einstein Ring. Exactly. So we can kind of see this galaxy that is behind another galaxy. Normally we won't be able to see it, but because the light is then distorted, we're kind of peering around behind the galaxy that's in the way. So this is a very, very cool thing. And again, this was not one of the main targets of Euclid. This was just a happy coincidence that in one of Euclid's first images, this was one of the things that appeared. Let me get rid of that again. So in one of Euclid's first images, there was this Einstein ring in the background, and a scientist was able to find it and then kind of zoom in, study it more closely. And this is very cool because it is one of the closest things we've ever found in terms of Einstein rings. So we've known that Einstein rings existed. We found some of them before, but we've never found one this close. So this is the closest Einstein ring we've been able to find to date. And this is very, very cool because it helps us study gravity. It helps us study two galaxies. And it helps us really confirm, just whacked my screen and the associated camera. It really helps us confirm that these Einstein rings are a thing, that gravity behaves the way we expect it to behave. So it's very, very cool. And again, this was not one of the main science objectives of Euclid. It's just a happy coincidence that this happened and that someone was able to notice it and observe it. So even though we don't yet have any of the cosmology results from Euclid, Euclid is still giving us some pretty cool information already. For an example, this Einstein ring. Question, hey David Dunn, you switched to Twitch. Hello from Twitch. I do indeed see Twitch comments as well. I usually focus on YouTube because that's where most of the viewership is, but I do see Twitch comments coming in as well. So if you're on Twitch, you can also say hi. Question here from Paul. I know there's a bunch of questions in between. I'm just focusing for now on the ones related specifically to this, to the Einstein ring. Then we'll go through the questions here, and then I'll talk about the other topic that I want to talk about that one of you has already mentioned here in the comments as well. Comment from Paul, are all gravitational rings Einstein rings, or are there all sorts of different rings? So usually you can have different types of gravitational lensing, but when you get this perfect ring, we call it an Einstein ring just to kind of pay homage to general relativity. So generally, if you have a complete ring, we call it an Einstein ring, but you could also just call it a gravitational ring. It would be equivalent, but we just call so all gravitational rings are indeed Einstein rings. That's just kind of the name we've given them, but you could also just call it a gravitational ring. A very cool question here from John. Can the ring be undistorted back to its original form? So not completely, but we can do a pretty good job of reconstructing the original galaxy based on what we see. And this is something we've already done, for example, with the Hubble Deep Field views that I was showing before, where we have these slightly distorted galaxies. A lot of effort is then done to kind of reconstruct the original shape of these galaxies. This is especially important for surveys that use weak lensing. For an example, the weak lensing experiments like KIDS, or even DES, the Dark Energy Survey. These are ones. Okay, David Dunn, that is a very cool image coming through on Twitch. Can I put this on screen? Let's see if this is going to appear well on screen. It is not going to appear well on screen. So for anyone on Twitch, there was just a like very happy face made out of distorted galaxies that they've posted on Twitch. It was very cute, but it doesn't show up on Restream. So if you want to see, I guess you have to join the Twitch chat as well as the YouTube one. So yeah, there's experiments like the dark energy survey or the kids experiment, which are weak lensing experiments. So they take a lot of images of these distorted galaxies, and part of the effort they do is then to try to reconstruct the initial galaxy. Because by reconstructing it, you can then study things about galaxy populations or the structure of matter in the universe. So we can convert these kind of distorted galaxies. There is a process to try to recover the original shape and structure of the galaxy, because that gives us a lot of information. It's not something that we can trivially do. Just look, it's not easy to do, or we can't just look at this Einstein ring and say, like, here's exactly what this original galaxy looked like. By having an Einstein ring, we can probably more accurately reconstruct the original galaxy than if we just have a part of the distortion, because the Einstein ring is really like, here's all of the galaxy just distorted completely. So there are processes to reconstruct the original galaxy, and this then gives us information about both galaxies. So it's pretty cool. Okay, sticking to this, and then I'll end sticking to this idea of recovering the original galaxy. James is asking the follow-up question of, can we do reverse math of these rings and determine what massive objects the light just passed around? And I'm going to link that to Sina's question of, what does Einstein ring represent other than the distortion of light due to gravitational effects? Why is it important? Both of these are excellent questions. And in the case of this Einstein ring that I'm showing you, it's very clear that there is one galaxy in the foreground and one galaxy in the background. However, sometimes we get these things where the object in the foreground is not necessarily clear. So we can, by seeing how much the light has been distorted of the distant galaxy, we can infer the mass of the object that did the distortion, because we can understand the gravitational field. So we can understand the mass of the object that caused this distortion. And this is very, very cool, because not all of the mass of a galaxy is contained in its visible matter. Stars only represent a small fraction of the mass of most galaxies. Most galaxies, to our knowledge, have a huge amount of dark matter, which is this mysterious type of matter that interacts via the gravitational force, but doesn't interact electromagnetically. This means that dark matter is essentially invisible to light. But because dark matter interacts gravitationally, dark matter can distort space-time, and therefore dark matter can cause these gravitational lenses. Just to make sure we're all on the same page here, the universe has three main components. Everything you see, everything you're accustomed to, everything from me to my tea mug to my cats to the stars you see at night. This is normal matter, and normal matter only accounts for about 4.9% of the energy budget of the observable universe. There's another 26.2% in the form of dark matter. Dark matter is this weird type of matter that interacts gravitationally but does not interact electromagnetically. So it is essentially invisible. It does not interact with light. Then we have 68.9% in the form of dark energy. Dark energy is this weird type of energy that is driving the accelerated expansion of the universe. And that's pretty much everything we know about dark energy. We get these very, very precise numbers from the cosmic microwave background radiation. This thing here. This is the oldest light we can see in the universe in any direction we look. This is a snapshot of what the universe looked like 380,000 years after the end of inflation. Orange bits here indicate slightly more energetic particles of light. Blue ones are slightly colder particles of light. This was formed in the very early universe when protons, electrons combined together to form the first atoms, and the particles of light, the photons, broke away, they decoupled, and they started traveling freely in the universe. Today, they make up this cosmic microwave background radiation. From this here, we can get the exact numbers that we had on this pie chart of 4.9% normal matter, 26.2% dark matter, 68.9% dark energy. Bringing it back to gravitational lenses, as you all know, I have to show the CMB at least once per stream. Took 25 minutes because someone in the comments said that me accidentally flashing it just now didn't count. So now you got a proper CMB. Bringing it back to the gravitational lenses, the reason this is important is because gravitational lenses really help us study dark matter. Because one of the few things that we know about dark matter is that it does interact gravitationally. Dark matter can distort space-time and can cause these gravitational lenses as well. So by finding these distorted galaxies, we can reconstruct the original galaxy. We can reconstruct what the lens was that caused the distortion. We can figure out the mass of the lens that caused the distortion. And if the mass of the lens doesn't align with what we visually see, then we can say there's probably something big and massive that we don't see, but is interacting gravitationally. Sounds a lot like dark matter. So while this particular Einstein ring did not shed a lot of information about dark matter, the idea is if we have enough of these lens galaxies, we are able to reconstruct properties or information about dark matter, and this is what weak lensing experiments do. They track the matter distribution in the universe via weak lensing, and they can use that to infer properties of dark matter, which is very, very cool. So why is the Einstein ring cool? It's cool because it's pretty. It's cool because it's another confirmation that gravity is behaving the way we expect it to behave. It lets us study multiple different galaxies that we might not be able to see otherwise, and they can potentially, these lenses, these rings can potentially help us understand dark matter, which is this weird type of matter that's in the universe. So they're pretty cool. I see that there's follow-up questions here that are very related. A question from John here: can the configuration of the Einstein ring tell much about the distribution of dark matter in the foreground? Yes. Assuming dark matter is involved in the distortion, which it probably is, this distortion that we see with the Einstein ring, like how far away it is from the initial galaxy, how distorted is this, how much shearing there is, or how slanted it is, or how much, kind of like how much is distorted. All of this gives us information about the thing that is the lens itself, the thing that is causing the distortion, which could potentially be dark matter. Follow-up comment by Brath. I've seen the question about dark energy. I will answer that in a minute as well. Sticking to the questions about galaxy rings. Question from Brath here: have we observed any same galaxy lens by more than one other galaxy? I'm not completely sure. I feel like at that point it becomes quite hard to distinguish, because we usually clump the thing that is causing the distortion together. So I guess your idea here is if we have a trail of galaxies and we're looking like 3 galaxies in a line and we want the light from the most far away one. I'm not sure if that's something we've been able to completely accurately say, like, oh, there's 3 lenses involved here. But what we often do is we clump it together and we say, all of this lensing is caused by a big something. This big something could be a cloud of dark matter, it could be a galaxy. So we kind of clump all of the lensing as being caused by one thing, even if that thing is made up of smaller things as well. It's like this whole thing is the lens, this whole galaxy is the lens. We don't say individual stars are causing the lens, we say this whole galaxy is a lens. If you have a cluster of galaxies, then you can say this cluster of galaxy is the lens as well. So you can always group it together as being like this big thing here is the thing that is causing this lensing effect. But then saying like how many galaxies are in this cluster of galaxy that is causing the lensing is going to be a next level question that will be a bit harder to answer. Okay, I'm just going to check that I got all of the questions about the lensing before we go on to the other questions. And of course, there is another topic I want to talk about today. Sticking with semi-related question by Ben here. Given that general relativity is the foundation of cosmology today, what is your opinion on why Einstein wasn't awarded his second Nobel on this achievement? Should it be given posthumously? Good question. Personally, I don't believe that Nobel Prizes are worth giving to anyone. I don't believe that the Nobel Prizes reflect fairly on scientific progress, and I don't think they necessarily reward the people who should be rewarded. That said, I think Einstein's general relativity is an amazing theory. It's an amazing model. Now, usually Nobel Prizes are not given for theories or models. They're given for proof of said theory or said model. Like, we didn't initially get a Nobel Prize for the idea of dark energy, but there was a Nobel Prize awarded to the first people who kind of measured that space-time was expanding in a way that's related to what we assume to be dark energy. There also wasn't a Nobel Prize for the prediction of gravitational waves, but there was a Nobel Prize given to the measurement of gravitational waves. So again, this is a way in which the the Nobel Prizes often reflect more on the people who do the observations or the people who can test the theories, and not necessarily the people who come up with the theories. Often they're shared between a bit of both. So I don't think the Nobel Prize should be given posthumously, because then it will just add even more to the fact that the people who win Nobel Prizes are always old white men, or 90% of the time. And this will kind of perpetuate that. I don't see any point in giving a Nobel Prize posthumously, other than to recognize the achievement. But we already do this by the fact that we call it Einstein's general relativity. So his name is already immortalized. Giving him a Nobel Prize wouldn't really change this much. So personally, I don't think there's any point in giving a Nobel Prize posthumously. I also don't think there's much point in giving Nobel Prizes in general. But I do feel like general relativity is a very good model, and we do recognize its importance in cosmology. Okay, let's see more questions, and then I'll go through all of the other ones. I see there's a very, very interesting question from Prathia. Come to that one. Sticking with the gravitational lens, let's see, where were we? We covered all of these. I covered the question about why we should care about gravitational lenses. I covered these questions. Let's see. Covered that one. Okay. A couple of questions here at the bottom. Yes, the smiling galaxy is in the link on Twitch. Thank you, David. I did see that. Yes, thank you. Question here from Prath. Not exactly what I meant, but that's an interesting configuration too. Okay, then I'm not completely sure what you mean. You followed up with. I mean, suppose there are 3 galaxies in a triangle, and observing one of the galaxies lends by 2 others. I feel like that then becomes a bit harder. So you want 3 galaxies in a triangle, and I guess if you want the galaxy to be distorted by 2 others, you kind of want us looking in this direction. I'm not completely sure how much you would be able to separate the distortion caused by the 2 individual galaxies, or if you would just group them together as these are causing a distortion. It also then becomes the thing, because gravity is very weak. In order for all of these galaxies to play a role, you'd need them to be either in the same line of sight or very close to each other. And it's quite hard to find 2 galaxies in the foreground blocking 1 in the background. You might find 1 galaxy in the foreground blocking 2 in the background, and then you get lensing from both of those galaxies. But the other configuration is less likely, I would say. But yes, that is a very cool question. But I would say in general, we group the lens as being 1 lens and not being multiple lenses. Comment from John here, sticking to this idea. Have there been studies that compare the mass of a galaxy determined by the lensing it causes and the mass determined by its rotation curves for a single target to see if they agree? For a single individual target, I believe the answer is yes. So we've definitely done this for clusters of galaxies, like comparing weak lensing with other means of measuring mass, like the motion of other objects around galaxies. As for rotation curves themselves, so a rotation curve, just to put this in context for everyone, a rotation curve shows you how stars in a galaxy move, how quickly stars in a galaxy move as you get further and further away from the center of the galaxy. And stars actually don't completely move the way we'd expect them to, and this is one of the biggest pieces of evidence we have for dark matter. So if you take an individual galaxy, you can kind of use the rotation curve to get an understanding of the mass of the galaxy, which also includes the dark matter. So then the question, can you use a weak lensing experiment, is another way of measuring the mass of a galaxy, and can you combine these? I would say yes. I'm not sure if this is something that has been done. And the reason, like at a bigger level, it has. We've done this in clusters of galaxies, but on the scale of individual galaxies, in order to get a rotation curve, you need a galaxy to be pretty close by. And in order to get weak lensing, we usually talk about having a galaxy in the foreground and a galaxy quite far away in the background. So I'm not sure if you would then be able to properly get enough information about the galaxy to reconstruct a rotation curve. So let me just verify this 1 sec. I'm just going to very quickly see if we have any rotation curves here. Let's see. I'm not sure if you can hear the cacophony of dogs that just started barking outside. Let me just see a minute. So the galaxy where we found this lens is NGC 6505. And I'm just going to see if we also happen to have any rotation curves for this exact galaxy, because that would be pretty cool. I don't think we have rotation curves for this exact galaxy. Let me just check again. Okay, so we don't have the rotation curve for the exact galaxy that this lens was captured on, but I'm not sure if there are any individual galaxies that we've been able to resolve perfectly well enough to compare these two. But we have been able to compare rotation curves and weak lensing on a larger scale, and they do tend to agree. But I'm not sure if we can do that on the individual scale of one galaxy. Okay, I think that's all the questions I've seen about gravitational lenses. If I've missed the question, please do ask again. As always, I don't deliberately ignore your questions, but I try to jump around a lot, and I was just filtering out questions that were not relevant right now. So if I didn't answer your question about gravitational lenses, please do ask again, and I will try to answer it if I see it pop up. Now, you can't hear the dogs. I have good noise cancellation. That is good to know. I have a pretty decent microphone, and it does do a pretty decent noise cancellation most of the time. So I imagine you can't hear the dogs, but yes. There was a question about ring galaxies, Scott. I guess I missed your question. Let me just see if I can find it. If not, please post it again. Yeah, I saw you ask a question about how long is a second in deep space. I didn't see you ask a question about rings. So if you want to ask that again, Scott, I will try to answer it. Yeah, I did not see your question about rings. I just saw your question about the second one. Okay, question from Prath here, following up about this. There's a question here from Prath of what does NGC stand for, because I always refer to galaxies as like NGC something. So it's a fair question to ask, what does NGC stand for? And I will get to this in a sec, because I'm just trying to remember myself what it stands for. Is it nebulous globular cluster? It is something like this. It's a legacy name. It's a legacy name that reflects the original discoveries of galaxies, I believe. But what does the NGC stand for? That is always a good question. Yes. NGC is New General Catalogue of Nebula of Clusters of Stars. So technically it should be NGC-NCS. So NGC is the New General Catalogue of Nebula and Clusters of Stars, abbreviated NGC. And it was the classification that was initially proposed in 1888 by Jean-Louis Emile Dreyer. And it is this initial classification because people weren't completely, when people started studying galaxies, they were all kind of classified as nebula or star clusters, and the actual name for galaxy came much later. So there was just this general catalogue, the New General Catalogue, and this is the convention that we use to name galaxies. So galaxies are usually given in a denomination of NGC and a number, and this is like New General Catalogue entry number this. So in the case of the galaxy that we were just looking at, it's New General Catalogue galaxy number 6505. So yes, NGC is just the New General Catalogue of Galaxies. I see I was busy checking, and two people already answered that question here. You guys were quicker than me. Thank you, Guadav and David. You two were definitely quicker getting that answer than I was. I was just reading Wikipedia. That's where so this is the thing. When I don't know an answer to a question, I ask the internet, and usually you get pretty good answers. Now you need to filter out the AI and these are the proposed answers, and just go to something more reliable like Wikipedia, and you generally get a good answer. So that's my approach to at least this type of question. You probably can't find good answers online to some of the questions, otherwise I'd be out of a job. But for some of questions, my trick when I don't know is to Google it, and often I find an answer. And Galaxy Quest ships are designated NTE, which means not the Enterprise. That is a cool way of designating things. Okay, the question from Scott that I missed somewhere: ring galaxies are still real and not just distorted regular galaxies. Yes, a ring galaxy is another thing entirely. A ring galaxy is a type of galaxy that has a ring-like structure, and this is due to the way that the galaxy formed. Some potential shockwave in the galaxy that pushes everything outwards and makes it look like a ring. So you can have individual galaxies that look like a ring. That is not the same thing as a gravitational ring or an Einstein ring galaxy. Different things, but ring galaxies do exist as well. Yes, as Sina is saying here, there is no such thing as artificial intelligence, just complicated machines. And I agree with this. Everything that we call artificial intelligence is not intelligent. It's glorified chat predictor or very good at doing linear algebra, multiplying matrices. There is no intelligence involved there. Okay, so covered a bunch of the questions about gravitational lenses. Now I'm going to scroll to the top. I'm going to go right to the top of the chat, and I'm going to go through the questions that I haven't yet answered. And then I'm going to talk about the second topic that I want to talk about that was already hinted at in a question here as well. So that's also something that I'm going to talk about in a minute. So bear with me as I just scroll to the top and go through all of the questions. There was a question from James about superneutrinos, which I wasn't able to give much of an answer to. And by then I'd already jumped into gravitational lenses, but then there's a question from Sina. What is a supernova, and can you tell us any new developments or discoveries in recent years? This is a very, very cool question. So a supernova is basically a star that's reached the end of its lifetime. A star is a constant battle. You have gravity pulling things inwards, and you have the pressure caused by burning hydrogen and helium together and heavier elements pushing things outwards. So it's this constant battle. As a star burns up all of its hydrogen to make helium, it can then gradually make heavier and heavier elements. You fuse helium together, you get lithium. You can gradually go up until you have things like carbon and oxygen and things like this inside stars, heavier elements. At this point, the gravity becomes quite strong. So when a star reaches the end of its lifetime, it runs out of fuel, it stops burning stuff. And at that point, two things happen. You get the central core collapsing and the outer layers being pushed away in an explosion. So it's like for momentarily the pressure wins, everything on the outside is pushed away in a massive explosion, and then what's left collapses to form a remnant. This explosion is what is known as the supernova. During this explosion, all of these heavier elements like carbon, nitrogen, oxygen will be pushed out throughout the galaxy. So this then sets a seed for other stars to form, and all of the carbon in we are basically made of carbon, hydrogen, oxygen, and nitrogen. All of our carbon, all of our oxygen, all of our nitrogen, all of these were formed in exploding stars. And this is why Carl Sagan and others always give this phrase, if you are stardust, we are all stardust, because all of our carbon was formed in stars that then exploded by a supernova. So a supernova is a star that's reached the end of its lifetime, it's exploded, and it pushes its outer layers out throughout the galaxy. And what's left behind, depending on how massive the star is, what's left behind is either a black hole, which is extremely dense, so dense not even light can escape, a neutron star, which is slightly less massive, slightly less dense, or a white dwarf. These are possible compact objects or very dense objects that are the remnants left behind after supernova. Supernova are very, very cool because they give us a lot of information about the origin of elements, and they are also very pretty to look at. Supernovas happen when stars reach the end of their lifetime, but they don't always happen in a way that we can see them. But if there were a supernova, a bright enough supernova happening close by to us, relatively close by in our galaxy, we could have a second sun in the night sky, which is very cool. You could imagine looking up and seeing a second bright glowing object in the night sky, or in daylight even, which is very, very cool. So as a development in supernova over the last 10, 15, 20 years, I think a lot of the information we gain about supernova right now is used to things like, we can use supernova to calibrate distances to galaxies. So because we know that supernovas explode with a specific amount of light, or they emit a specific amount of light during their explosion, we can use them as kind of light bulbs or standard candles to figure out distances to galaxies, which is pretty useful and pretty cool. Helps us measure the expansion rate of the universe, things like that. Another cool thing about supernovas, when they explode, they emit neutrinos as well as a lot of other components, and neutrinos travel pretty much unhindered towards us. So this gives us what we call multi-messenger approach, where we can study supernova via neutrinos, via photons, and via other heavy particles that have been emitted. I'm not sure what are the major advances in supernova over the last 10, 15, 20 years, other than we found a lot more of them. We have whole catalogs of supernova now, which is really helping us measure distances and expansion rate in the universe. And the more supernova we study, the more we understand about how nuclear fusion happens inside stars. But I'm not sure about specific advancements that have happened in supernovas because that's not exactly what I work on. It's a bit too small scale for cosmology, but we can use populations of supernova to measure the expansion rate of the universe. So that's pretty cool. Comment here from Scott. I think it's like once you start fusing iron, it's like a fraction of a second before supernova. Yeah, iron is very, very heavy. And as soon as you don't even reach the stage of fusing iron, when you reach that stage, the star already starts to collapse. As Scott just pointed out here, the iron core doesn't fuse, it starts to collect. Yeah, so you produce iron, but you can't go above iron in standard stars. So you produce iron and then the iron just sits there. And this is what will then eventually trigger the supernova. Okay, sticking with supernova, comment from David here, like when Betelgeuse finally decides to blow up. Yes, Betelgeuse is a star not too far away. It's in Orion's constellation. You know, the Orion, yeah, the constellation of Orion, the Hunter. One of the arms of the Hunter is Betelgeuse, a bright orange star. It will go supernova at some point, hasn't done yet. And a couple of years ago, it looked like Betelgeuse might go supernova. It didn't. But it will be cool when it eventually does, but it's probably not going to happen for at least like 100 years. Coming from Guadav here, nearby supernova, no thank you. I don't want a distant star to ionize and strip my atmosphere and bombard me with high energy particles. Yes. So depending how close the supernova is, it could also be potentially very dangerous for life on Earth. So, you know, we don't want the sun to go supernova. The sun is not big enough. It's never going to go supernova. It's just going to end up as a red giant. So we don't want our sun to go supernova. We don't want a star that's very close by to go supernova. But if it's the other side of the galaxy, it might be cool. But yeah, if it's too close, it could have potentially very damaging consequences to us. Comment from Prasia, how are supernova different from nova and kilonova? Basically the amount of energy. So yeah, it's just the amount of energy, basically. So if you have more energy, you're going to be a supernova, and then a nova is much less energy. There's different ways of classifying explosions within the universe, within stars. Yeah, comment here from Scott that Betelgeuse might already have gone supernova centuries ago, but because it takes 600 light years, so it takes 600 years for light from Betelgeuse to reach us, it would take a while for us to know. So if Betelgeuse exploded 20 years ago, 100 years ago, 200 years ago, we still wouldn't know about this. This tea is so cold by now, I should have finished this tea a long time ago. It's like, this tea was made 55 minutes ago. It is cold. Okay, I have just finished off my tea. Yes, Betelgeuse does mean shoulder of the giant, I believe, in Arabic. I'm not completely sure about that, but I think it does, yes. Okay, so yes, stars reach the end of their lifetime. They collapse, they explode, they produce a huge amount of energy, and they source all of the carbon, oxygen, and things like that throughout the universe, which is very, very cool. Question from John here, sticking with supernova. Wasn't there an idea to look for supernova duplicate by a gravitational lens and the timing delay between them? Gravitational lens, I am not sure. I've not heard of that. Let me think that through a sec. So a duplicate of a okay, so you want to use a gravitational lens to find the supernova kind of twice, two images of the same supernova. To my knowledge, this has not been done, but this would be very, very cool. This would be very cool if you could use a gravitational lens to get multiple images of a distant object, and that distant object happened to be a supernova. That would be pretty cool. I'm not sure if that has actually happened, if we have any examples of that, but it seems like it would be a pretty cool thing to do. Yeah, so John, I'm not sure if we've seen any clear examples of that, but it is a very cool idea. That's my question. Okay, let's see. So that was the question of what are supernova. That was a very good question there, Sina. Thank you for that question. So now, where were we? Going back through the top, I'm going to do some quick questions, and then I'm going to go on to the second thing that I did want to mention today. That is something that someone specifically asked me to discuss today. And I'm just going to very slightly adjust my camera. That's better. My camera used to stay still, but now I have cats, so my camera moves a bit every week, and it just needs minor adjustments. I just realized it was a bit too off. My face was not centered. Okay, let's see. We answered these questions. There was a comment from David Howden that I do want to address at some point, which is related to the second topic I wanted to talk about. So I will come back to that, but sticking with other questions as well. Let's see. Then there's a question from Prath. Starts with, I got nerded like by a meme account yesterday. Let's see where this goes. Does a particle that's 1 Planck length long experience length contraction when it's moving? So this is a very cool question here, Prath. Now, a Planck length is the smallest distance we can conceive of. There is this idea that we can always divide space into smaller and smaller things. You know, you can divide a meter into centimeters, you can divide that into millimeters. You can keep dividing things down to angstroms and 10 to the minus whatever until you reach the Planck length. The Planck length is the smallest quantity of length that we can conceive of within the universe. However, what we cannot consider is a particle having a specific size. Now, particles are not classical objects, particles are quantum objects, which means you can't really say a particle is here. It's kind of like a particle is in this cloud. And then if you want to talk about the radius or the size of a particle, you usually talk about the size of this probability cloud. So how likely is it to find an electron, for an example, within a specific radius? But it's very hard to say, like, look, here's a particle of this size, because it's quite hard to attribute a size to something that is a quantum object. Then the second part of the question, or the question you actually asked, does a particle that's of this specific length experience length contraction when it's moving? So length contraction is an effect of general relativity, whereby objects that travel almost at the speed of light will experience, or at the speed of light, will experience the passage of time differently. Basically, the faster an object is traveling, the more it can experience length contraction and time dilation. So time moves slower, lengths contract. However, if you want to apply time dilation and length contraction to a particle, you run into a problem that gravity is something that we have a very good description of on large scales, but putting gravity together with small scales, or understanding how gravity works on particle scales, or even on the Planck lengths, is very, very difficult, because we would need a theory of quantum gravity in order to do that, and we do not have that yet. So, yes. The question here, I think, is a great question, Prath. My answer would be you cannot quantify the exact size of a particle, so we cannot say a particle is 1 Planck length. And even then, discussing if an individual particle experiences length contraction or time dilation becomes very complicated, because we don't know how gravity works on subatomic scales. We have very good understanding on large scales. We think gravity is this distortion of space-time. Objects in space follow the curvature of space-time. Objects with mass tell space-time how to bend. But trying to understand this on the quantum size is very, very, very difficult. So that's a very cool question, Prath, but I don't have a clear answer for that. Other than, that's very cool. But I would say no. No, we can't talk about length contraction for a particle of any length, because we don't know how to put gravity together with a quantum world. It's coming from David Dunn here that there has indeed been a supernova seen in a gravitational lens. I did not know that. That is very cool. So a lens gravitational, so a supernova that's seen through a lens. So that is very cool. Thank you for sharing that link. So I'm just going to put this on the screen for anyone watching on YouTube. There's a link that should be here on the screen. This is what David Dunn just posted on Twitch. So if you go to the Keck Observatory SN Zwicky Supernova Zwicky, apparently this is a supernova that has been gravitationally lensed, so we have seen multiple occurrences of the same supernova. That is a very cool fact. I'm going to go read this later, but if anyone wants to grab the link, you can grab the link from here. It should be on your screen on whatever device is kind of like here in this banner. It should be the comment. So thank you for sharing that link. That's a very cool thing. I have not heard of that. It makes sense that if you have a supernova, bright star exploding, you can have gravitational lensing of it. So it makes sense that we've done this. it just was not in my mind that we had done this. This is probably something I knew at some point, and then that information was lost to me. David here saying that it's up to me to figure out quantum gravity. Quantum gravity is above my pay grade. I am happy not working on quantum gravity. I think quantum gravity is going to require a lot of effort from a lot of people before we figure it out. It's not something that one individual person is going to figure out, but it is a very, very cool topic to work on, just not one that I want to work on. Okay, so that was a very cool question there, Prath, about quantum gravity and basically how gravity works on the quantum scale. We don't have an answer to that, but it is very, very cool. Okay, there's a comment from Scott here. I remember asking how long a second is in deep space, far away from any gravity, and if we could work backwards to calculate it. And there's a Kurzgesagt video that said it's a ridiculously small amount shorter. Yeah, so because we know that time is relative, time is influenced by gravitational fields. If you go to a place where there is absolutely no gravity affecting anything in the universe, is 1 second there still what we call 1 second here? Probably not. And a Kurzgesagt video recently calculated this. That is very cool. For anyone who doesn't know, Kurzgesagt is a very cool YouTube channel, and the one that I'm actually wearing today, I'm wearing their hoodie. The second best science outreach channel, obviously behind my own, of course. You know, they have 20 million followers, but mine are detail. So yeah, if you want more cool science outreach, go follow Kurzgesagt. That is Kurzgesagt in a nutshell. It's a very cool YouTube channel, and their hoodie is very comfy and cozy and supports their things. So that's cool. Okay, there was a question from Junior Gandalf at some point. Do aliens exist? Absolutely, I am sure they do. But then it depends what you mean by aliens, right? Because do I expect that there are little green men walking among us? No. However, if we consider alien to be any life form that is not on Earth, I am sure that exists in the universe, just a question of probability. You know, we are one planet adrift in the universe. There are thousands of planets in our galaxy. There are millions of galaxies in the universe. There are also moons that could host any type of life form. So I think there are going to be other life forms in the universe. There might even be life forms elsewhere in the solar system, like on some of the moons around Jupiter or around Saturn, have the right qualities where they could host some type of microorganisms. So I think there are definitely going to be other life forms in the universe. Now, if you're asking if there are any advanced civilizations as advanced or more advanced than us, that becomes increasingly less and less likely, because in order to have advanced civilizations, you need a lot of things to happen and a lot of things to not happen. For an example, if you have random supernovas, or if you have there's a lot of things in the universe like gamma ray bursts or supernovas that can wipe out life on planets. So in order to have another civilization advanced like us, you would need a lot of things to happen. In my opinion, the universe is very, very big. That's not an opinion. The universe is very, very big. So in my opinion, it's quite likely that somewhere else in the universe there is an intelligent species. However, I don't think we're likely to interact with them anytime soon. Because in order for us to be able to interact with any civilization that is advanced and not just like a microorganism, we need a lot of things to happen, right? We need a lot of things to not happen, like no close by supernova, no close by gamma ray. And then you also want this civilization to be close enough that we can actually visit each other or exchange information. And this becomes less and less likely. So are there aliens? Or do aliens exist was the question. I would say there are definitely life forms in the universe apart from us. We haven't found any yet. However, I don't think any of these life forms that we are going to find within the next 100 years are going to be advanced civilizations, but I will be happy to be proven wrong about that one. Maybe someday. Okay, going through the questions, I think then we jump straight. There were a lot of galaxy lensing questions. So I think I've answered all of those. Let me just make a note of another question I'm going to answer in a sec. And then I will carry on. I'm somewhere in the comments. Let me just catch up. And then I will jump back to the bottom. Okay. So we answered all of those questions. We answered about ring galaxies. We did a lot about ring galaxies. We answered the question about what NGCs are. And then we answered about nearby supernova. That was a very cool conversation. Okay, here we are at the bottom. let's see. We discussed comment here from David when we were talking about supernova being lensed. There was a comment from David Dunn. Because the path lengths are different, the supernova goes off several times. Yeah, that makes sense, because when you have a gravitational lens, the different parts, the different light beams are going to take slightly different paths, and they don't necessarily arrive at the same time. So this means you can see the same supernova happening multiple times via gravitational lensing. So you might see imagine you have the lens here, so you see the supernova in these 2 points. It might be that it reaches this point first, so the supernova goes off here, and then it goes off here. And this is the same supernova, but because you have this gravitational lens, and the arrival time is different, you get to see the supernova more than once, which is very, very cool. Also, if you don't do so yet, please do go follow David Dunn either on YouTube or on Twitch. I believe on Twitch these days, because David Dunn has a very cool astronomy show as well. So go follow David Dunn on all platforms. Keeping to this, comment from Paul here. If different observers see different length and mass particles, this is not related to the lensing, sorry. If different observers see different length and mass particles, can one observer see that a black hole formed while another observer sees that it did not? Yes. Everything in the universe is relative. Time is relative. Events happening inside the universe are relative. So having a black hole collapse is something that we might see here, and another distant observer might not yet see it, or might see it at a different time. So there's this idea in general relativity that simultaneity is not really a well-defined concept. Two objects happening or two events happening simultaneously is not well defined, because it depends on the observer and the motion of the observer. So it can absolutely be that two different observers look at a supernova, for an example, and one observer sees it go off, one doesn't. So one observer could see that a black hole has formed, while another observer wouldn't see a black hole forming yet. But I realize now that your question is not about when we see events, but could you be in a situation where I see a black hole has happened and another observer would never see that black hole? And there I would say no, because even though different observers see different lengths and different masses of particles, the formation of a black hole is an event that happens when certain conditions are met, and these conditions do not depend on the observers. So even I would say that we might notice that a black hole has formed at different times. There might be a big gap between us seeing a black hole and someone else seeing a black hole form. But I would say if the conditions for the black hole to form are met, eventually all observers that can see the black hole or the object will eventually see said black hole. So the formation of the black hole itself should not depend on the observer. Okay, I have a couple other questions that I want to answer. And then there's still the other topic that I want to talk about. So there was the question early on from Sina about dark energy when I showed this pie chart, and the question was just, can you repeat what dark energy is? So dark energy is a big component of the universe. Dark energy accounts for 69% of the observable budget, or of the energy budget of the observable universe. What we know about dark energy is that it is pushing the universe outwards. It is acting as kind of an anti-gravity on large scales, and it is making objects move away from each other in the universe faster than they were before. So we know that the universe is expanding, and we've been able to see over the last 30 years that this expansion is accelerating. It didn't start accelerating 30 years ago, we've just been able to study it for the last 30 years. Our best explanation that we have so far for this additional expansion of the universe, this accelerated expansion of the universe, is dark energy. So dark energy has kind of negative pressure. Instead, it pushes things outwards, but not a lot is known about dark energy. There are some ideas that could dark energy be a fifth force. So we know the universe has 4 forces: gravity, electromagnetism, strong nuclear force, weak nuclear force. Could dark energy be a fifth force? Could dark energy be some type of particle? Probably not, because of the way it dilutes throughout the universe. So it behaves like an energy density, like an energy component. But not much is known about dark energy, other than it seems to be driving the accelerated expansion of the universe. And without dark energy, or without something behaving like dark energy, this image, the cosmic microwave background radiation, would look very different. So based on this map here, or this picture of what the universe looked like 380,000 years after the end of inflation, so 13.4 billion years ago from our perspective, based on this yeah, based on how this figure looks here, we know that dark energy needs to be a thing, or at least something behaving like dark energy needs to be a thing in the universe. And we know it needs to account for about 69% of the energy budget of the observable universe. As to what dark energy is, we're still trying to figure that out. But there's a lot of ideas, there's a lot of possibilities, but we haven't yet understood dark energy. So that's my summary of what dark energy is. Okay. Follow up here from Sina. Isn't the expansion of the universe to this day caused by the aftermath of the Big Bang? Not anymore. So we did have this initial event that caused the expansion of the universe, which, let me just go to my map of the history of the universe, or my schematic of the history of the universe. So let's go to the actual nicer one of the two, this one here. We had this kind of initial inflation period where the universe at some point was something that we don't know what it was. We call it a singularity because we can't really explain it with our current equations. Then inflation happened. During inflation, the universe started expanding really, really quickly. Everything in the universe was pushed away from everything else in the universe really, really quickly. This is this page of cosmic inflation that we had in the very early universe. Then the universe, once inflation stopped, and we know that inflation stopped at some point. So once inflation stopped, the universe carried on drifting away. It carries on expanding. However, when you no longer have the source of this inflation, you no longer have the energy driving this, the universe should gradually slow down, because we have a lot of gravity, we have a lot of massive objects. So gravity is gradually going to bring things together. So this is something you can see here in this figure. We have this initial expansion, this inflation, and then everything gradually gets kind of pretty constant. Let me actually go to this one here, because I think this one is slightly nicer for the point I'm making. After this initial period of inflation, we have things like dark ages, development of galaxies, and you can see that this expands pretty much constantly. It doesn't really expand exponentially. It just expands constantly. And there was this idea that eventually this expansion should slow down. But what we've been able to see is that over the last million years or so, billion years or so, this expansion has increased. This expansion has started accelerating. So instead of slowing down due to all of the gravity, this expansion is speeding up again. We need something else to explain this speeding up, and this something else is dark energy. So while the expansion of the universe was initially triggered by inflation, once inflation stopped, this expansion should have run out eventually. It slowed down. It didn't completely slow down, it just kind of stagnated, and then at some point dark energy becomes the dominant component of the universe, and it speeds up again. So you can think of dark energy today as triggering cosmic inflation 2.0, like a new cosmic inflation. The mechanism, we believe, is slightly different. The energy involved is different, and the scales involved are different. So generally, we don't think that it's the same mechanism that triggered inflation and that is triggering the accelerated expansion today, but the behavior is pretty similar. So yes, hope that answers that question. Follow up here from Scott. I still think that there's something behind the increased rate of expansion, meaning that there's a direct correlation between empty space creating dark energy. Have to think about that a bit more. I'm not completely sure what you mean now. Okay, comment from Ben here. If dark energy didn't exist, would we be able to define the center of the universe? No. So the main reason why we can't define the center of the universe is because to define the center, you're one, assuming that the universe is finite, whereas as far as we know, the universe is infinite. The universe is bigger than we can possibly comprehend. So you can't really put a center to something that is infinitely big. If you could put a center, you could also put edges or a boundary. And that's not the case. The universe doesn't have edges or boundary. You can put a center to the observable universe, because the observable universe, by definition, is everything we can observe, everything that has had time to send us information. So the observable universe is always centered around the observer. So our observable universe is centered around us. However, then you have the kind of the observable, the universe as a whole, and that does not have a center. This is also when we go back and we talk about inflation, or the Big Bang, if you want. There's also this question of, was there a center to the Big Bang? And there wasn't. And this is a common misconception, that the Big Bang was an explosion. And an explosion does have a center and origin. However, the Big Bang, or this initial inflation, was not an explosion, it was an expansion, which means every part of the universe was its own center of expansion. So everything in the universe moved away from everything else in the universe. Every point in space-time was the center of an expansion around it. So there isn't a definitive center of the universe. Every point in the universe pushed away from every other point. So this is independent of dark energy. So we cannot define the center of the universe because the universe has no center, and this does not depend on dark energy. But the center of the observable universe will always be you. You will always be the center of your own observable universe, which is also very cool. I think there was another question that I saw here that I wanted to get to. Okay, I answered that one. We got into a brief conversation about AI that I glossed over there. Okay. Yeah, there was some comments here. A comment from Gwyneth that I didn't mention, that when I made the offhand comment about AI, Gwyneth made the comment of not about AI, about ring galaxies and the shockwave in the whole galaxy. Gwyneth mentioned that galactic level shockwave sounds so cool, and events so large it affects an entire galaxy. Imagine the energy involved. Yeah, it's very cool. It's a very dramatic process, but it is very, very cool. Okay, there was another question that I wanted to answer, and then I'll get to the other topic that I wanted to discuss. We covered nearby supernova. Let's see, what else? I feel like there was another question. We were talking about lens supernova, which was very cool. Then I jumped into this idea of what are supernova, what are dark energy. Right, there was another question from Sina here that I wanted to get back to. Seen a lot of cool questions today, as you promised there would be. So, question from Sina a while ago. Maybe it sounds really sci-fi, off to a great start. But I want to ask, can a wormhole exist on planet Earth, which means under the effect of gravitational waves here? In principle, no. So I believe in the previous stream I talked about wormholes. Hang on one sec. There's just like cat noise, cat mischief happening, but it's fine. They're pretty calm right now, actually. One of them is sleeping. They switch which one is sleeping now. So I think the main thing with wormholes is they're something that theoretically could exist or mathematically could exist, but they're quite hard to realize in our universe. A wormhole is a solution to general relativity, something you can pull out of the equations, but it's not something that can really happen in any meaningful way. And even if a wormhole did exist, it would immediately collapse if there was any matter going through it. So if you want to have a wormhole on planet Earth, it would immediately collapse due to the gravitational pull of Earth itself, if it's on Earth. If you want to make a wormhole kind of close to the Earth, you could do that, but as soon as anything went inside this wormhole, the wormhole would cease to exist. But yeah, I think in the previous stream 2 weeks ago, I did talk about, or 3 weeks ago now, I did also talk about wormholes, just based on the fact that the last page of my notes has a wormhole drawn on it. So I believe last week we were talking about black holes, or the last stream, there was a conversation about black holes, white holes, and wormholes. So I won't go into too much detail about that now. Okay, there was a comment from John that they found a new bacteria on the space station. I have not seen that, but that does not surprise me. We humans keep bringing more bacteria to the space station, but I have not seen that. Okay, let's see, going quickly through the last few questions here, and then I'm going to discuss the other thing I wanted to discuss today, which is hinted at, and which David Howden made a comment about early on in the stream, like 5 minutes into the stream. There's a comment here from Scott. The more expansion, the more dark energy. Then dark energy causes more expansion. I'm not sure how you would get. Yeah, I'm not sure how you would make that work. I'll think about it, but I'm not sure how you would make that work. Okay. Comment here from David Howden. The Yannis cats are quantum entangled. If one is sleeping, we know the other is awake. Not necessarily. Sometimes they're both awake and up to mischief. Sometimes they're both sleeping. But usually in the evenings, one is awake, one is sleeping. But unless they both decide it's mischief time, and then they're both awake. But yeah, the one that was sleeping on the cat tree is now walking around, and the one that was sat on my laptop is now sleeping on the sofa. So they have switched during the stream. And I'm sure pretty soon the other one's going to wake up and they're going to want to play together, mainly because I think the one who's walking around is going to jump on the other one. That often happens. Okay, so one more thing I wanted to address. And there was a comment from David Howden earlier as well about this. So I want to talk about asteroids and asteroids potentially hitting Earth. So an asteroid is basically just a chunk of rock somewhere in the universe that could come close by or could not come by. You know, we have asteroid belts, which by the way are very, very empty. If you're ever flying through an asteroid belt, you would see on average like one asteroid every few days. But that doesn't lend itself to good sci-fi. So in sci-fi, you see people dodging asteroids. That's in an asteroid belt. That's not realistic. There's still a lot of empty space in between asteroids. But point being here, there's a lot of asteroids that are potentially on a collision course with Earth. Now, a lot of these are small. A lot of the vast majority of these will pass by the Earth without us even noticing. A lot of them would burn up in our atmosphere. But then there's the thing of, can an asteroid hit the Earth? Could there be an extinction level event caused by an asteroid? Yes. This has happened before. We know the dinosaurs were wiped out by an asteroid. This was a mass extinction level event, massive asteroid falling on the planet. So we know that asteroids can hit the planet. This is something that has happened before. We've also seen it on much smaller scale. Sometimes we see these asteroids that are small and just you see a light trail in the night sky. Maybe in a city you hear a crash. You go to a field, there's a small rock. Most things that come through will burn up in our atmosphere. They will not make it to the ground. But there is always a possibility that an asteroid could someday hit the planet. You need the asteroid and the planet to be on the same kind of path and meet at the same time. There's also the fact that the universe is... Hello. My cat's got zoomies. One sec. Do you want me to throw this for you? I've just been given a toy and I'm supposed to throw it. Go fetch. Okay, yeah, he'll bring it back. He likes playing fetch. But yes, okay. So, yeah, space is very, very big. Space is very empty, but also space is very difficult to track. Asteroids are very difficult to track. So there's a lot of asteroids, a lot of rocks in the universe or in our solar system that we have been able to track, and there's a lot that we haven't yet been able to track. Usually, if a rock is big enough that it could cause an extinction level event, we're going to see it coming. We're going to see it before it hits us. So why am I... He's just lost his mouse under a cupboard. This is a tragedy. Oh, he managed to get it back. You're now getting cat updates because Good is playing. Okay, so asteroids. There's a lot of asteroids. And the reason I'm bringing this up today is because there's been a bit of press about asteroids recently. Specifically, a couple months ago, like in December, a new asteroid was discovered. Now, it's not a new asteroid, it's just we newly discovered this asteroid. And this is an asteroid that is currently moving away from the sun, and it's going to swing back around. It's in orbit around the sun, like us, on a completely different path, but a different orbit. But based on the data that people collected in December, this asteroid is going to have a close encounter with Earth in 2032. In December 2032 specifically, which is 7 years from now. So hang on one sec. I have indeed been given the mouse back. He plays fetch. Go fetch. He'll bring it back again. He brings me the mouse. He does this at 3 a.m. as well. This is the game. He brings me the mouse, I throw it, he brings it back. So if you have ever wondered if a cat plays fetch, yes, he does. This one in particular does. This is good there, by the way. Okay, so where was I? I lost my trail of thought there twice. Asteroids, yes. So based on the data that we collected from this asteroid in December, it seems like this asteroid is going to be in close proximity to Earth in December 2032. So what does close proximity mean? Close proximity means it can be anywhere between 6 times the distance between the planet and the moon, our moon, or 1 times the distance or anything closer. So there could really be a close approach could not mean anything. We have close approaches from asteroids pretty frequently, and we don't even notice because they pass us by. They pass 10 times further away than the moon does, and this is still considered a close approach or a flyby. However, When we discover an asteroid for the first time, there's a lot of uncertainty because we still need more data to be able to track it properly. So this means that it very, very quickly, once we discover an asteroid and we know that it's on a trajectory, a specific trajectory, scientists calculate the impact probability. So how likely is it that an asteroid is going to impact the Earth? And once you calculate this, usually you get a ridiculously small number. There's only a handful of asteroids that have more than a 1% chance of hitting the Earth, and we're tracking them, all of the ones that we're aware of. So when we discover a new asteroid, there's a lot of uncertainty, there's a lot of unknown, and it can take a while for us to get clarity about what is going to happen with this asteroid. And this means that in the early days, the probability forecast of how likely it is that this asteroid is going to hit us is going to be constantly changing. So why am I bringing this up? There is an asteroid known as 2024 YR4. 2024 because it was discovered in December 2024. YR4 is just the designation it's given. So asteroid 2024 YR4 is somewhere between 40 and 90 meters in distance, which means it's either the size of an average apartment. Yeah, it's like take a couple of apartments, kind of that size. 90 meters is considerably bigger. So what does this mean? If an asteroid that is about 40 to 90 meters were going to hit the Earth, what would happen? So if it hits in an ocean, it could trigger a small tsunami, not a dramatically big tsunami, but a small one. However, if an asteroid of this size were to fall on a populated area, if it's closer to the 40 meters in diameter size, it would produce a shockwave that would probably smash all of the windows in the city, probably do a bit of damage to the first building it landed on, but not much else. However, if it's a 90-meter asteroid, it can probably damage a pretty wide area of a city. So this type of asteroid size is advertised as a city killer because it could have the potential to wipe out a city. So I'm talking in general terms here. So we know that asteroid 2024 YR4 was discovered in December 2024, and we know that its size is somewhere between 40 and 90 meters in diameter, which is a pretty big range. So here's where things get interesting. When this was first discovered, they calculated the probability of it hitting the Earth to be about 1%, or about 0.5%. Then in mid-January, or in early February, the chance of this asteroid hitting the Earth in 2032 went up to 3%. And that's a big jump. So this obviously then hit the press, and the press, in popular science articles and in a lot of places, this was reported as city killer asteroid, 3% chance of impact in 2032. However, since then we've got more information, and the chance of impact has now been reduced to less than 1%. It's down to about 0.3%, which means if this happened 1,000 times, it would hit us 3 of them. So this is a very, very, very low chance. So there's a couple of things to unpack here. One of them is that our defenses, our ability to track these asteroids is working. We found this asteroid 8 years before it is due to come close to the Earth. And within the span of 2 months, we've already been able to get enough information on it to say that it is very, very, very unlikely that it is going to hit the Earth. It is now being tracked. It is now entering the kind of asteroid database that we have to track what is happening, which means we now have a good understanding of it, and we will get even better understanding. In about 2 years, it's going to be so far away from us that we're not going to be able to get more information. Then in about 2028, it will come back around as it orbits the sun. It will come back around to a point where we can get more information, and then we still have 4 years before a potential, very small possible impact. So one takeaway here is that our tracking is working. We're getting good at figuring out where asteroids are and where they're going. Another takeaway is that in early days of tracking an asteroid, information can change very, very, very quickly. The probability of impact can increase and can decrease. This is something that is going to happen. So when we first discover an asteroid, if within days of discovering an asteroid, there's the comment of there's a 3% chance that it's going to hit Earth, take that with a pinch of salt, because that is likely to decrease. And if you're wondering how it increased and then decreased, I'm going to draw you a slight diagram. So let's just imagine this here is the Earth, and that's the Earth, and here's an asteroid. Okay, we start here. We have the Earth and we have an asteroid. Okay, so the things that can happen at one point, you might say, like the asteroid, we don't know where its path is going, so its path in 8 years is anywhere in this triangle, in this region. So then you calculate all of the places the asteroid could be in 2032, and you say, okay, there's a 1% chance it's going to hit the Earth, just based on where it is. That's your first data point. Then you get more information about the asteroid, so this triangle is going to narrow. So your second one might be like this. So this is now the second one, the one that's a bit stronger. So you've got more information, so the possible path of shrank. So now the Earth occupies a much bigger space in this possible place where the asteroid is going to hit, which means the probability is going to increase. So when our trajectory was up here, like this first triangle, it was 1%, then it went down, it went to 3%. Obviously, none of this is to scale. This is just to give you the idea. However, then when we get even more information, which is what has happened now it's something like this. So let me just draw it here. These are the thicker lines that I'm drawing now. So now we've got more information, and we've gone from here to here, which means now it looks like it might even miss the Earth, depending where it is. So now it goes down to a 0.3% chance. So this is how, as you get more information about the path of an asteroid, it can first get bigger and then get smaller. This doesn't mean there's a 3% chance that the asteroid is going to hit us. It meant based on that level of data we had, there was a 3% chance. Now that we've got more information, it's a 0.3% chance. So this is very, very common in early stages of finding asteroids. And I wanted to talk about this today because there were all of these articles in the news of city killer asteroid is going to hit the Earth in 8 years with a 3% chance, or might hit the Earth. I think that it was phrases like city killer asteroid might hit the Earth. Even when it was at 3%, might hit the Earth is an exaggeration. But this is something that is good. Not an asteroid hitting Earth, I'm not saying that is good, but the fact that we've been able to measure it 8 years in advance, we've been able to track it, and now the chance of it hitting us is down to like 0.3%. So the reason I'm bringing this up is because it was in the news, and someone asked, can I talk today about the chances of us being hit by an asteroid? There's always a non-zero chance that we're going to be hit by an asteroid. However, this one in particular is not very likely to hit the Earth. And even if it does, it will wipe out a city. It's not going to be an extinction level event. To put it in context, the asteroid that wiped out the dinosaurs was several kilometers in distance. We're talking here about something that is less than 100 meters. So it's a couple of orders of magnitude smaller. It is not something that we need to be overly worried about. I've seen the people who work on asteroids be asked, like, does this keep you up at night? And they've all said, like, no. I don't think you need to be worried about an asteroid wiping out life on Earth anytime soon. Okay, so, and as Paul is just saying here in the comments, please go watch the movie Don't Look Up if you haven't watched it already. It's always a very relevant film to go watch. It is kind of funny as well. So, short answer, no, you shouldn't be worried about an asteroid, and no, specifically asteroid 2024 YR4 is not likely to hit us in 8 years. Follow-up from Scott, I heard that one wasn't very scientifically accurate. Yeah, the film Don't Look Up is not in any way scientifically accurate, but it's a political commentary. It's not meant to be scientifically accurate. Armageddon is not scientifically accurate either, but it's funny. Also not a political commentary, just funny. But Don't Look Up is more, you don't watch it for scientific accuracy, you watch it for its critique of society. And because it's just funny. Okay, so going back to the questions here, when I started talking about this, a comment from Prath, you missed out on the wormhole discussion. Not really, my wormhole discussion today was small. 2 weeks ago there was a wormhole discussion about black holes and white holes. I think you were there for. You probably even asked a wormhole question, but today I just very briefly glossed over wormholes. Okay. Let's see. There's a bunch of very good comments here. As always, I'm just focusing on things that have a question mark. If you don't put a question mark, I filter through it. I assume it's not a question. But I see there were some very interesting comments here from Guadav about converting matter and energy into darker energy. Cool ideas. You need to read them properly. Okay. So comment from Prath, how big was the dinosaur or the dinosaur kilometer? A couple of kilometers, I think about 10. I see people joking about, 8 years is a lot of time. 8 years from now, we don't know what's going to be happening. Hopefully, more things will be sorted out. Hopefully, the world will be in a better place 8 years from now, but we will see. Okay, and I see people saying, considering the way things have been going, I, for one, welcome destruction via asteroid. There's better ways to go. And, yeah. Maybe let's not hope for the eradication of all life on Earth, just something. Or no, let's not hope for any of that, right? We don't want to be wiped out by an asteroid. We don't want the planet to be. Coming from Paul, we should arrange a cup of cosmology session to end just before the asteroid's point of closest approach. Okay. If cup of cosmology is still ongoing 8 years from now, I will try to do a cup of cosmology when the asteroid is at its closest approach. We can do that. We can watch the asteroid come towards us together. Okay. Let's see, more comments here. Were there more comments or more questions? We've been going for over 90 minutes now. This has been a very long stream. There was a comment from Paul talking about the asteroid. This is a good lesson in what the word probability really means. In this case, it means how much we know, since the actual asteroid path doesn't change. Exactly. So when we change our probability estimates from 1% to 3% to 0.3%, it's not that the asteroid suddenly changed direction. It didn't go like, actually, I'm going to go here instead. It's just our understanding of it changed, our knowledge of it changed, and this changes the prediction, the probability, and our estimates. Okay, I think that was all of the questions there are coming from Sina. The only way to avoid this asteroid is to participate in the song contest and show them what we got. I'm not sure if we can sing the asteroid away, but let's all try. Let's go for it. Okay, very quickly, there was a comment from Ben. Could the introduction of human-made artificial satellites affect an asteroid's trajectory as it passes Earth? Yes. There is, in fact, an idea called DART. DART stands for... what did DART stand for again? It's a very cool acronym, and I've forgotten the acronym. One sec. So DART is this idea... Double asteroid redirection test. That was what DART was. Double asteroid redirection test. Also, if you Google it, you get a very cool effect where things happen on screen. So there is this idea of actually having this kind of Earth protection mechanism where we would have artificial satellites that if an asteroid came close by or close enough, these artificial satellites would bump into them very slightly and distort just enough to move the asteroid off course so it would pass by the Earth. This is something that was already tested with the DART mission, where it just very slightly bumped into a small rock and moved it slightly. 8 years is a long time. By then, we might have a more advanced version of using artificial satellites to slightly push things away. It is something that we could potentially do. And it is something that people are looking into. Okay. When I mentioned Armageddon, there was someone who angrily said, or like passionately defended, Armageddon was based on a true story of a real hero. John McClane is a man of many talents, indeed. Yes, I do like Armageddon. It is funny. It is also a film that is used in science circles to see how many scientific inaccuracies you can spot. And I believe the record is like 137 or something like that. So yeah, Armageddon is fun. And it is funny to rewatch. I've watched it lots of times, but I would not take any of it to be in any way scientifically accurate, but it is fun. Okay. Then there are, the Rick and Morty reference, I'm afraid, is lost on me because I actually have not watched Rick and Morty. It is just not my thing. So if you make any Rick and Morty references, they will be lost on me. There probably is a drinking game of drink for every scientific inaccuracy in Armageddon, but I wouldn't recommend it because there's a lot of them. If you take a shot of water every time, you will be very well hydrated, which, is good. You should always be well hydrated. Okay, wrapping up. 95 minutes in. This has been a very long stream today. I even thought today maybe I do a shorter stream because I kind of want to wrap things up today, but that didn't happen. But that's fine because it's been super cool questions. There is a comment from Prati. I'm not sure if you have time to do this, but have you considered editing snippets of these streams for shorts? Yes, I have. So there was a couple months ago, like a year ago, I started dropping hints that maybe something new was coming for Cup of Cosmology, that something was going to happen. My plan was and still is that someday Cup of Cosmology is going to expand into YouTube Shorts or Instagram videos, kind of short streams. The problem with this is it requires a lot of time and a lot of effort. And I don't have time and I don't have energy. There is also the thing that, I like Cup of Cosmology. I've been doing it for 10 years, but it is a hobby. It is something I do in my free time. I am not paid to do Cup of Cosmology. And if I get to the stage where I want to be making videos that are kind of, that I can upload as shorts and that I can put out there, it's going to be a lot of work. And right now I'm not sure if it's something that I can commit to. So it is in the works. There is a Cup of Cosmology Instagram account locked down. You can go follow Cup of Cosmology on Instagram. It's currently not a very active account, but it exists. And yeah, at some point there potentially will be Cup of Cosmology shorts. There's also the problem that in the current format I do live videos, which is the nature of Cup of Cosmology. It's live. And there's a lot of people, a lot of science outreach people, science communicators who already have that kind of short format down. And for me, I feel like that moves away from the interactive nature of Cup of Cosmology. This is going to get into a very long answer. Short version, but yes, I have thought about making Cup of Cosmology shorts, calling it maybe a shot of cosmology, but I feel like that's not going to happen within the next couple of months. It's something that it's on the long-term plans, but don't expect it anytime soon. Let's go with that. So yes, but no is my answer. Yes, I've thought about it. I've thought about it a lot, but it's not going to happen anytime soon. And just making this very clear, this is not me asking for advice on how to edit videos. I know how to edit videos. It's a question of I don't have time or energy. But it is a very, very cool suggestion, Preth, and it is something that I am thinking about. There might be a further update on that at some point soon on Cosmic Scales. Okay, so yeah, a quick question from Guadav. What happened to the poster in the background? It's over there. I just shifted around. At some point, I realized that my layout in my living room didn't make sense. There was also the thing that none of you ever saw, but before every stream, I used to have to kind of move my light to be behind my screen and then move it back to be a lamp for the sofa. Now it's much easier. So I moved my whole apartment around, and that means that I no longer have the poster behind me. It's up there. But I also decided it's better because the poster was very dark, and when I wear dark clothes on a dark chair with a dark poster, I was just kind of like a floating head. So there are plans to put more stuff here. I have the cat tree, which I had advertised for a long time, but there is a plan to put something up here. I just haven't done it yet. There is actually a poster up there. It's just out of sight. So I do need to put some stuff there. Yes. Okay, so an hour and 40 minutes. This is on the way to be one of the longest streams in quite a while. This has been super fun. There's been a bunch of cool questions here. We've had a lot of regulars, a couple of new faces coming in with new questions. So thank you everyone for being here. This really has been super, super fun. I've enjoyed all of the questions, all of the comments. We did cover the two topics I wanted to discuss, which is Euclid measured a ring supernova, which is very, very cool. And an asteroid is not going to hit us anytime soon. Don't worry about it, which is also a good thing to be aware of. But also we talked about a lot of cool topics as well. There was a lot of discussion of supernova, about dark energy, quantum gravity came up, wormholes. It's always so fun. So I appreciate all of your questions. I appreciate all of your comments. As always, I appreciate you all for being here. Wo ist der Katze? Katze ist da. Ein Katze ist da. Der andere ist da. I have one cat there, one cat there. There you go. This is why my camera moves. There is a cat there, in a ball, in a hammock, and the other one is on the sofa sleeping as well. Cat and cat. Katze. Okay, as I was saying, thank you everyone for joining. This has been super, super fun. Cup of Cosmology will not be online next Sunday. I won't be doing a stream next Sunday. I will be busy. In fact, next Sunday I'm celebrating Christmas, part 2. Fun family story there. Christmas is next Sunday. So next Sunday I won't be online. Cup of Cosmology will be back 2 weeks from now, same time as always. That is 7 p.m. if you're in Europe, 8 p.m. if you're in Finland, 1 p.m. if you're on the east coast of the US, 10 a.m. if you're on the west coast of the US. As always, there is a time zone converter on cupofcosmology.com where you can figure out when the next stream is in your own time zone. Of course, you can also subscribe to the YouTube channel to make sure you get notified before I go live. And while you're at it, if you haven't done so already, please do like this video, subscribe, leave a comment, do all of the usual stuff. It really does help boost engagement. Cup of Cosmology will be back in 2 weeks. In the meantime, feel free to reach out. There's an email address, contact@cupofcosmology.com. You can reach out also on Mastodon. I am dchooper91_Cosmo at astrodon.social. You can reach out there as well if you want to chat. So thank you everyone for joining. This really has been really fun. Cup of Cosmology will be back in 2 weeks. I hope to see you all then. And I hope in the meantime, you'll take care of each other and stay curious.